This is the second video of the moments topic, and we are dealing with stability. So essentially, I think I left you with an idea at the end of the last topic, at the end of the last video, that talked about how we had a beam that, if it were supported in the middle, it would be balanced. I mean, if we perfectly placed it in the middle, it would be balanced. Now, that makes sense intuitively to all of you, but why might that be? We need to make sure, mathematically, we can prove that. Well, what you can assume to start with is that the weight on either side is the same, or you have as much weight on this side pulling down in a clockwise direction as you've got on this side pulling down in an anti-clockwise direction. So we could start considering every little bit and adding up to loads and loads of moments, an infinite amount of moments. Or what you can say is that you can say that there is a point at which all the mass, the weight, sorry, of this object acts through. And that point we describe as the centre of mass. So if you like, this is the point the weight of the object acts through. Okay, and if we can assume there is that point in which the weight of the object is acting, then we can work out our moment. So let's look at our clockwise moment. Well, the moment, which is the force, this times the weight times the distance, is going to be the weight of the object multiplied by, well, we're interested in the perpendicular distance from the pivot, which happens to be 0. And so therefore our product is 0. In other words, there is no moment, so there is no turning force. Okay, let's see if this makes more sense, if that was a bit tricky to understand. Let's imagine we've got our same weight with the same centre of mass, same beam, sorry, with the same centre of mass of weight, and now we move the pivot to one side a little bit. Now, what do you think is going to happen in this case? Well, we know it's going to topple in a clockwise direction. However, the law of moments can tell us why it does that, because, in effect, we now have a distance and a weight around the pivot, and therefore that's going to create a clockwise moment for us. A clockwise moment's a force times the distance, or the weight times the distance. So therefore it will topple. It will rotate down in a clockwise direction. So I think I have given you this problem in class, but let's imagine we had a retort stand, and this retort stand it's quite heavy in actual fact. We're actually going to find out the weight by using this technique. Giving you one 50-gram mass, and then what we've done is we've balanced the retort stand with the 50-gram mass. Now you know the 50-gram mass is a huge distance away comparatively to where the centre of mass is, because it's so light compared to such a heavy object. Remember, this is the point where the weight of the object acts. At this point we have a 50-gram mass. So I did some readings, and I wanted to work out what the weight was. And I suspended this 50-gram mass at 1 metre from the pivot, and I measured this distance, which was very small. It was just 1 centimetre between where the pivot is and where we measured the centre of mass to be. So let's measure the weight. Okay then, let's use this equation like we always do. And let's look at now, in order for it to be balanced, the anti-clockwise moments must equal the clockwise moments. So what we're going to do is we're going to look at the clockwise moments first. We need to bear in mind, of course, that 50 grams is not a weight, it's a mass. So therefore we need to convert this into kilograms and then multiply it by g, because weight is mass times g, which equals our weight, which is going to give us 0.5 newtons. So therefore we've got 0.5 newtons times the 1 metre, and the weight of our object multiplied by 1 centimetre, which is 0.01. Rearranging gives us 0.5 times 1 divided by 0.01, and that gives us a grand total of, if I'm not mistaken, something like 5, I believe. 0.01 gives us something like 50 newtons. So that is the weight of our retort stand. About what's that? Yeah, that's about 5 kilograms. A bit heavy, but nonetheless, the maths is correct. Now, with that in mind, this concept of centre of mass, we can go back to those bridge problems which we dealt with, and I will deal with them once more as a bit of revision, and also to include a centre of mass term. Here is a very simple bridge. We have 2 people standing on it. It's being supported. Let's give some dimensions first before we show you where they are. It's 20 meters across from end to end. And we have 1 person standing at this end of 400 newtons. That's quite light. The bridge itself weighs 2,000 newtons. And another person here, slightly heavier, at 600 newtons. Okay, so this looks like a fairly straightforward problem, but the only thing you need to start considering is actually the bridge has weight. So you need to include another point, which is the centre of mass of the bridge, so therefore this is where the weight acts, which we've got as 2,000 newtons. Now where's that going to be? Well, this is a nice uniform bridge, it's quite an even bridge, so we're going to say it's slap bang in the middle, so we know that's at 10 meters. This person sitting at 5 meters from one side, this person sitting at 5 meters from the other side. I think I've given you too much information there. No, that's absolutely fine, because what we're going to do is we're going to look at the force exerted on this support. Okay, so running out a little bit of space here, but let me try and cram it into the bottom. This point we're going to take as the pivot, and we're going to look at all the clockwise moments acting from these 3 weights, and then we're going to balance that with the anti-clockwise moment exerted by the force of Fy. So let's work that out. We have, to start with, we've got 400 newtons times by the 5 meters. We then have 2,000 newtons by the 10 meters, because it's halfway along that plank. Then we have the 600 newtons, and not to be confused, it's not from this side, it's from the pivot, so that's going to be 15 meters. And of course that must equal the anti-clockwise moment, which is the force, y, times the full 20 meters. Okay, working that out very, very swiftly, this side comes to 31,000 Newton meters, and we'll divide that by 20, giving us Fy as 1,550 newtons. Superb. So now what's the force on this side? Let's call it Fx. Well, simply the total weight of all these people must be supported by the 2 pillars. So if I've got 1,550 on one side, then the other side must be the difference between the sum of the weights and Fy. So if I can write that in very delicately, Fx is going to be 400 plus the 2,000 plus the 600 minus the support weight on this side, 1,550, and that is 1,450 newtons. Okay, so there are some sums with how you'd work out using the centre of mass. Just bear in mind you're either given the place of the centre of mass, or you assume if it's an equal object where it's going to be sitting in the middle. Good, now there are ways to, that's as far as the calculation is concerned. Now there are ways to discover where the centre of mass is. That's what we're going to talk about now. So this is how you find the centre of mass of what we call a laminar object. So COM, centre of mass. Let's imagine we had a strange shape. Well, it's not that strange, but let's just imagine we did. And we've cut a few holes in them, in this object. Now this can be an irregular object, it can be weighted with a strange weight on one side, half can be made of one material, half can be made of another material, it doesn't matter which, but this technique is always correct. So first of all, you need to suspend the object from a point. It needs to be free to move and I'll tell you why. Because what happens is if this becomes our pivot, then this object is going to swing back and forth freely until there is no moment acting. And if we think about where our weight is, let's imagine that is our centre of mass there, which weight acts. This is our perpendicular distance from the... Sorry, this is the line of action. Actually, let's start using that term a little bit more. Line of action, i.e. the point, the line that's extended from the direction of the force. And because there is no perpendicular distance, this thing will not experience a turning moment anti-clockwise or clockwise, so therefore it stays stationary. So in effect, it will always come to rest object comes to rest when the weight is below, sorry, let's be more precise, centre of mass is below the pivot. Okay, so therefore you're going to have a line down here where you know the centre of mass is going to be. Then what you do is you then suspend from a second point and repeat. So now let's imagine I've now changed this object round. There's my first pin and that's my line that I've drawn in. Then I suspend it from another point and I get a similar line of action that I draw in. The place where they come together is the centre of mass. Lines cross the centre of mass. Okay, I suppose the question is, how do you draw that line? Well, we use what's known as a plumb line. So in essence, it's a piece of string attached to the point which you're pivoting around, and it's got a weight at the bottom, and it suspends itself vertically with gravity. So this is called a plumb line. So it's to work out a point which is vertical. Okay, now with that in mind, having found that, now we need to talk about stability. And when do things topple over? Well, if we had our simple box on the ground, and we're imagining this as a nice uniform box, then if I were to move it at an angle, there's my centre of mass, suddenly we have a pivot, which is the edge of the box, and we have this line of action showing where the weight acts. And at this point here, you see there is a perpendicular distance. So therefore it will feel an anti-clockwise moment. That anti-clockwise moment tips it back the right way. So this will turn upright. However, if we tip it a little bit further, then suddenly our line of action goes beyond the pivot, and so now I have a clockwise moment, so this falls over. Okay, so that's very simply what happens with stability. There is a point of no return here where this moves across the pivot, and therefore it will fall over, or if it doesn't quite fall, it bounces back upright. So I suppose we need to comment then on how to make something more stable. Well, this is an object which is very stable comparatively. Let me just draw the comparison. And there's two reasons why. Firstly, if you have a larger surface area, then the pivot is so much further away from the centre of mass, it has to turn a greater amount before the line of action falls over the pivot. And two, you need to lower the centre of mass. So if you can lower that as far as possible, then again you'd have to lift it further before you get to a point in which the centre of mass line of action goes beyond the pivot. So those are your two ways of making an object more stable.